Hello, and welcome to the latest instalment of Ask a Nerd, the show that takes a deep dive look into the automotive industry and the technologies involved in delivering zero emissions vehicles and the energy transition. We hope you're enjoying these shows, and we've got another cracking one for you today. So a couple of reminders before we get going whilst our presenters are in the green room. We do record all of these episodes and they're available via our YouTube channel at Greenplates ZEV. Please support us by subscribing to the channel and hitting those like buttons. It all helps to support our mission to distribute good quality auto industry information with integrity. Ultimately, though, we're here for you, and we're most interested in what you want to know more about. So don't forget to post your questions via that website too. Now, ever since the dawn of the automotive industry, engineers like us have been trying to work with the laws of physics to get cars moving along the road and through the air efficiently. Whether that car's powered by fuel or electricity, an efficient aerodynamic design will help it to travel further on a finite amount of energy. If we look back to the 1990s and GM's first effort at an electric vehicle, the EV1, that vehicle had a coefficient of drag of 0.21. Outside of EVs, we have the VW XL1, again focused on efficiency, brought that figure down to 0.19. Fast forward to today, Mercedes' recent EQXX electric vehicle concept brings that figure further down to 0.17. Now, as we know, it's not just about CD, so let's hop right in and hand over to Cecile to introduce our guest for today.
Hello. Thanks, Tom. So if, like me, you follow the news on electric vehicle, you must have noticed that recently a lot of the announcements are talking about the aerodynamic and are giving what they call the CD. And I have asked myself what could be the implication between the aerodynamic of the car and how it can enable some of the battery and EV technology, and vice versa, how this battery technology can maybe change the aerodynamic of a car. So to answer this question, today we are going to ask a nerd, and we have a special guest. So before I present our guest today, I'm going to explain how it's organized. So we will have, again, an educational part with some battery and EV technology and how they interact with the aerodynamic. We will go through some case studies with the Volkswagen ID.3, a Ford F-150, and the Aptera, and we will talk about EV and aero trend. Meanwhile, you can ask any question and your comment to Tom in the chat, and Tom will come at the end of this presentation to ask your question to our guest. So without further waiting, today we are welcoming Wouter Remmerie. Hi, Wouter. Can you present yourself?
Hey, Cecile and Tom. Yeah, thanks for the introduction and thanks for inviting me. My name is Wouter and I'm the founder of AirShaper, which is an online platform where people can upload a 3D model to run aerodynamic simulations in a very easy and accessible way. And this means that we're in contact with people from the drone industry, from the car industry, athletes going faster on skis, cyclists. Those are all domains that relate to aerodynamics, because whenever you want to go fast or more efficient or further, aerodynamics quickly comes into play. As soon as you go above speeds of 20, 30 kilometers per hour, it starts to play a role. And especially for electric vehicles at highway speeds, it's the most dominant factor in terms of where you're spending your energy. So getting it right makes a lot of sense. It's very clear why Mercedes and GM and so on are focusing so much on getting the CD value down.
Okay. Can you briefly explain what sort of studies you have made and how you end up to be in this industry very quickly?
Yes, my background is in mechanical engineering, so actually not in aerodynamics, even though we got a short course on that topic. I first worked on gearboxes for the wind turbine industry, so those large things generating renewable energy. And then in my free time, I designed a car, a patented concept with internal and external air channels. We got it patented together with the company. We got to talk to Ferrari and Pagani and so on, which was really nice. And then I spent 6 years doing projects, all kinds of engineering projects in the wind tunnel, doing wind tunnel tests, also doing simulations, thermal simulations, NASCAR formula simulations, and so on. And then I thought, well, this is all very nice and interesting, but it's a bit repetitive, and there's a threshold for people to get into aerodynamics. You have to buy expensive software, expensive hardware, and so on. So I founded AirShaper to be an online platform to make it more accessible, and that's how I got into this industry. And now, because it's a generic platform, we see all kinds of applications. And today we're talking about EVs, which is a big focus point for us as well.
Okay, so preparing this episode, I have tried to find information about how the aerodynamic of the car have evolved depending on the year. And we can see here a graph with this evolution. We can see that there are several disruptive and improvement of this aerodynamic. So obviously, the lower you are, the best your aerodynamic is. And we have seen recently several EV featuring really very good value. So Lucid came with 0.21, Lightyear came with 0.20, and very recently, Mercedes says that they can be 0.17. One question I have asked myself is what it can represent. And as an order of magnitude, I found a paper published by Volkswagen and talking about the ID3, saying that by improving the CD by 0.01, they were able to gain about 6 kilometer range. So that's what they say in this publication to give an order of magnitude. The first thing I would like, Wouter, is can you explain what is the aerodynamic and what represents this number CD and why is that, how it works?
Yeah. So in the end, the thing that is holding you back or that is causing you to spend energy is the total drag force on a car. So if you're pushing your car forward at a constant speed or you're accelerating or decelerating, but if it's at a constant speed, you have to push the air away, and this comes with a certain resistance force, and this is the aerodynamic drag. That's the one that will determine your fuel consumption or energy consumption, and eventually your range combined with the rolling resistance of the vehicle. But that drag is made up of a number of things. First of all, there's the aerodynamic efficiency, and that's the CD coefficient. That is an indication of how efficient the shape is relative to its size. So it's actually normalized by the size, which means if you have a very streamlined drop shape, which is 2 kilometers wide, for example, it has a huge amount of drag because it's so big, but it's still very efficient because the shape is efficient. So the CD coefficient is actually normalized by the area or the frontal area of the object. And then there's the frontal area of the object, which you have to multiply with the coefficient to obtain the total drag on your object. So that's two very interesting parameters. So there's a CD coefficient, and you see all those numbers like the XL1 of Volkswagen, all those concept cars and so on. They talk about CD, but what's very important is to also take into account how big that car is, which is indicated by the frontal surface area A. So you can have a very efficient car in terms of CD coefficient, but if it's an SUV and it's still huge, then the total drag is still larger than a smaller, perhaps less efficient vehicle in terms of CD. So it's very important to always talk about CDA, which is the product of the efficiency and the size of a vehicle when comparing different vehicles. And then what we also see in this formula on the screen is that your drag coefficient also relates to the velocity. So this relation says that if you double your velocity, your drag force will be multiplied by a factor 4. And that's the drag force. Now, to know what kind of power consumption you need, you again have to multiply with velocity. So that's a relationship between power for aerodynamics and velocity. That's the third power of velocity. And that means if you're going at 100 kilometers per hour and you need maybe 100 kilowatts to propel your vehicle, that's too much, but just as an indication. If you go to 200 kilometers per hour, you would need 800, which is a factor 8 in terms of power. And that's why aerodynamics are so important. If you double the speed, the power requirement goes up by a factor 8. And this explains why a car with maybe an engine of 100 or 200 horsepower can reach up to 200 kilometers per hour, but the Bugatti Chiron needs 1,600 horsepower to actually just double the speed to 400 and a bit. And so that's crucial. That's why aerodynamics plays such a key role for electric vehicles.
So you talk about racing and high-performance car. If we come back to more normal car, obviously we have bigger drag force, and I have tried to get an idea of ballpark how it is distributed. So ballpark, I understand that the top of the car would be about half of this, the bottom would be about a fourth, and around the wheel would be also about a fourth. Obviously, when you are on a racing car, you can make a lot of design things and it works, I'm going to say, nicely. But when you are on a commercial car, it's slightly more difficult. So what can we do on a normal car? I have noticed several things that are common nowadays. So for example, on the Tesla, I have noticed that it's also more and more common on a lot of cars to get this sharp angle at the rear. So I have the impression that it gets the flow narrowed on the rear of the vehicle. You have obviously things around the mirror. A lot of work are done here, and I think we all know that a lot of drag force comes from the mirror. Also, something we have very common nowadays to get this nice flat door handle. So it looks like something posh, something luxurious, but it's actually very useful for the aerodynamic.
Yes.
And the last thing I have noticed on this slide is about the wheels. So I know a lot of Tesla owners find these wheels very ugly, but I understand it gets some implication in terms of the aerodynamic. So I don't know if you can talk about some of these features a little bit.
Yes. So indeed, we were talking about electric cars today, so maybe we can focus on why it's so different for electric cars. So one of the things that has been not overlooked, but has not been in focus in the past is the underfloor of the car. So the air goes on top of the car via the right side, but it also goes underneath the car. And with a normal combustion engine vehicle, there's a lot of components there. There's the drive shaft, for example. There's heat components. There's shielding. There's a differential, and so on. A lot of these components are exposed to the airflow. So a car may look very smooth at the top, but underneath it can be very messy. And all that flow that has to go underneath the car will hit these things, and this is an obstruction, and this is blocking the airflow underneath the car. So you're dragging more air along as the car passes over this air. So cleaning up the underfloor of a car is a very, very nice way to lower the drag coefficient, because first of all, you don't have to take into account all the visual constraints. Because very often, if you touch the outside of the car, it's a huge, I'm not going to say battle, but collaboration between designers and engineers fighting for aerodynamic performance and aesthetics. At the bottom of the car, you don't have such a compromise all the time. So that's really nice.
Yeah, that's true.
Another thing is that electric drivetrains don't require so much components at the underfloor. So you have the big flat battery pack. You have small electric motors which can be put in different positions. On some cars, even in the wheels. I believe the Lightyear does so. I'm not sure, we'd have to check this. Which means you have a lot more freedom to actually design a clean, flat underfloor. So that's one big problem that you can tackle with electric vehicles. Another thing is the global shape of a car. So one of the first things you start with when designing a car is to draw the silhouette of the car, the nice 2D shape when looking at it from the side, like you see the Tesla pictures on this slide. And there's a lot more freedom there as well, because packaging-wise, you can play around with different battery modules. As said, the small electric motors can be put in more interesting positions. You don't have as many constraints as you do with a combustion engine car. So the basic shape can also be changed, which you can see on the EQXX, the Lightyear, and so on, which have very long, low tails at the rear. The bonnet has different proportions, and so on. Then at the front, there's the radiator, but I think we'll cover that in the next slide. This one.
Exactly.
So cooling, I'll just jump ahead for a second, but cooling is also very important. Electric vehicles are much more efficient. So if you have
here we have an example of how the aerodynamic of the car can impact some of the technologies that are inside the vehicle, because obviously you are touching the thermal management of the vehicle, you are touching the cooling of not only the cabin, but also it gets implication for the cooling of the battery, and how you make this aerodynamic can change some of the technology you can choose on your thermal strategy.
Yeah, exactly. So an electric vehicle is very efficient. If you carry energy on board, let's say 90% of that energy ends up as power at the wheels. With a combustion engine, it's maybe 30, 40, 50% in Formula One of that energy that actually ends up at the wheels. And all the rest is waste heat via the radiator, via the exhaust, and so on. So you need to dispose of that heat, which means you need a big radiator. For electric vehicles, there's far less heat that you need to dispose of. So you can have a smaller radiator. On the other hand, there's a smaller temperature bandwidth in some cases that you can play with, because the batteries need to maintain a certain range for the temperature. It cannot be too hot, cannot be too cold. And those limits are often more demanding than those for combustion engine cooling liquids. So it's a balance between more efficient drivetrains, but more demanding temperature constraints. If you want to go back to the previous slide, you also mentioned the wheels on the previous slide. So wheels are indeed very important. We're optimizing wheels for customers or wheel rim designers, and this is true. When you Google this, you'll see that adding these covers can extend your range by 3 to 4%, or reduce consumption by 3 to 4%, which is a lot, which is really a lot. And of course, they don't always look as nice, but this is the case. So it's really important. And the reason for this is that they act like a big mixer. They chop up the airflow, which is causing a lot of turbulence, as you can see on the Tesla pictures. There we did a test to shield the wheels of the Tesla Model S, and this really gave interesting gains in terms of drag coefficient. So that was pretty good.
Something we talk about the thermal management, and you say the radiator and so on. Something we see now more common on EV are active shutters. So when you have this air coming inside the car, obviously it's not good for the aerodynamic, but you want this air for the thermal management. But sometimes when the thermal management is not critical, you do not want to penalize your aerodynamic, so you want to shut this stuff.
Yes.
And then we see a lot of car manufacturer using active shutters. So this example is from the Volkswagen ID3. I guess these active shutters are made by Plastic Omnium, and they can get a sort of curtain that can open and close through the whole stuff, so letting air to enter and block it when needed. Is that something you discuss with some of your customers and you have seen more and more in EV, or?
Yeah, indeed. So the basic concept is that if the grill is open, then the air will pass through, and it has to be forced through the radiator. And the radiator is a huge component with a lot of very fine metal pieces, which increase the surface to exchange heat. That's what they do, which means you have a lot of fine channels with a lot of friction. So pushing air through the radiator represents a big source of energy loss. So if you don't need it, as you said, you can actually shut these and make the vehicle more efficient. You'll also have a cleaner front of the vehicle, so you're creating less turbulences, even though you're at the front where you have stagnation zone. It's not too critical, but still, this provides a cleaner airflow to the rest of the car. And also, when you have a radiator, there's always an exit. So you cannot push air into a radiator and just have it disappear. When air goes in, air needs to go out. And this exit air can also disturb the flow, whether it's underneath the car or via the wheel wells or via some exit holes. This also disturbs the air and can increase the drag coefficient. So blocking that channel when you don't need the cooling is indeed a very common strategy.
So talking about the battery now, it's not obvious, but some of the battery technology can also impact the aerodynamic and vice versa, because you say that the bottom of the car, the underneath, is very important. And obviously, usually on most of the modern EV, you have a flat battery, what we call a skateboard. And the position of this battery may affect very highly the aerodynamic of the car. This is something we have talked in one of the previous episodes, so actually episode 3 with David White from Deneca. And we discussed the fact that there is a difference between the Tesla and the Lucid, because Tesla get cooling in between the cells, while Lucid have chosen a cooling plate, and this cooling plate get actually a thickness, and this thickness makes the battery pack a little bit thicker. And David explained in this episode that it penalizes a little bit the drag of the Lucy. So is that something you can confirm, that this even small thickness, because we are talking about here, I don't know, about 5-8 millimeters, something like that, can it really impact so much the drag force of the vehicle?
Well, it depends on where that ends up. If you say everything above the battery pack needs to shift up, then you have a higher frontal surface area of the vehicle. So if
But
you
it can
have,
put the passenger upper. So for the comfort of the passenger, it can be a penalty.
yeah, exactly. Yeah, so it's a mix of comfort for passengers, visibility, where the greenhouse will be positioned. So if the whole vehicle grows in height, then you grow the frontal surface area, and you can actually increase the drag coefficient. But of course, these things are very marginal. Just 1 centimeter is a very small thing, but still, they're looking at every possible detail to make this happen. And it could be that by making a thicker battery pack, maybe they can shorten it and have a better diffuser and splitter at the front and the rear of the car, and again improve the airflow. So one penalty in this location can mean a benefit in the other location in terms of aerodynamics, because very often different regions of the car are connected in terms of airflow.
I think the battery technology and the way to make the package is something not very understood by most of people, because any of the technology you are going to choose in your battery pack, like to choose to put a bus bar instead of a cable where you have something more structure, or decide that you will put a second floor on the battery, or decide you put in the Taycan here, you have what they call the Fuse garage. Get a lot of implication in terms of packaging, what you have in terms of all the technology you have. And this is also why we see a very different shape, especially the racing car are very different, because we have this flat battery for, I'm going to say, normal and commercial car, but most of the time the racing car do not have these flat batteries. They're very often a chest. So like, for example, in the Rimac, this is the case, or like in Formula E or whatever, they don't have these flat batteries for different reasons, packaging, but that have impacts on the battery. And here on the example I put, we can see also, as you have discussed, Wouter, a compromise with the comfort of people who are sitting and the flatness, I'm going to say, of the batteries. Another example I put is something I have reviewed on my website, a recent patent published by Ferrari, where they have a battery in 2 stages. So one is a chest and another one is relatively flat. And something they really insist on the patent is that this battery is not completely flat. So they put a small angle on between the chest and the flat part. They say in this patent the optimal angle is 3 degrees, whatever. But they explain that this gives them some benefit for the aerodynamic of the car and also downforce. So can you explain a little bit how this would work in this case, for example?
Yeah. So in general, the way, or one of the main ways to generate downforce on sports cars and race cars, counterintuitively, is to actually get more airflow underneath the car. You would think this is going to make the car surf on top of the air and lift it, but it's not the case. If you push air underneath the car and it accelerates, because it's like a contracting funnel, if air accelerates because of the Bernoulli equation, it means that the pressure goes down if the velocity goes up, which means that if you have a low pressure underneath the car, the entire bottom of the car will act as a suction surface, pulling the car down, generating downforce. And to increase this acceleration of the air, there's a number of things you can do. At the front, you need a good front splitter design, which means you have a nice entry channel of the air, and you can actually see this the front splitter in the image you have there, the flat horizontal bit at the nose. That's where the air dives underneath the car. Then you need a very flat underfloor to not obstruct the air and to allow it to travel fast. And at the rear of the car, you want to actually make the floor go up again. So this is actually an area where you are connecting the rear wake area behind the car with the airflow underneath the car, pulling the air underneath from the car, helping it to accelerate. So it's the front splitter, the flat underfloor, and the diffuser at the rear that all work together to accelerate this flow. And this angle of the diffuser at the rear of the car is actually quite critical. If it's too steep, the air will not follow the angle of the diffuser as it comes up, but it will separate and create turbulences. If it's too flat, you don't have enough power to actually pull the air underneath the car. So this angle is quite critical. So I can actually understand why they would say, maybe in their case, for this specific car or something, 3 degrees can be quite useful. And in the past, you would have the engine at the rear of the car. Of course, you still have an engine in some of the hybrid Ferraris, but the length and the angle of the diffuser are very critical parameters. And if you can balance them by maybe making a longer diffuser and a softer angle, you can actually get more performance or vice versa.
Okay. So we talk a lot about the bottom of the electric vehicle. And when we were preparing this episode, you mentioned the fact that the Taycan is a very good example, but unfortunately I didn't have time to change that. So I've still kept my Volkswagen ID3. And in one of the papers they published, they talk a lot about how they have tried to clean and get some flatness and get, as you say, everything is not here constrained by design. You can do whatever you want. And they explain in this paper what they have done. They explain also about the diffuser. And they give some order of magnitude. So as I say, they say the CD with this clattering can be improved by 0.010 and between 0 and 0.025, which can give them up to 15 kilometer additional range, which is relatively a lot for an electric vehicle. So again, if you can comment about that, you have already said a lot, but this is something you see commonly right now.
Yeah, indeed. So at the front, you have the area where the air dives underneath the car. And this needs to be a smooth transition so it doesn't get disturbed and already becomes turbulent at the very beginning. So that entry that you see here is actually quite important. Through the center of the car, it's relatively easy to have a nicely attached airflow, but the more you get closer to the wheels, the more difficult it becomes. Especially the front wheels, because they rotate, they need a lot of room. So the wheel wells are actually quite wide, which means that as the air dives underneath the car at left and right, there's suddenly an opening on top. So the wheel wells and the air wants to enter the wheel wells, but then it hits the end of the wheel well and needs to dive underneath the car again to be aligned with the underfloor. Which means that this air is hitting all of the suspension components because they are right in the middle of the airflow. So the air hits the suspension components, creates a lot of turbulence, and then dives underneath and continues, and then sees the rear suspension, and there it happens all over again. So if you can shield the components that the air will see, that's actually quite important to reduce drag, to keep the air more laminar, and to keep it flowing at a higher velocity. And indeed, you mentioned the Porsche Taycan. What we see here on the Volkswagen is that they put some cladding on the suspension components, so it actually nicely dives underneath them. On the Porsche, this cladding has been extended to actually cover the entire gap of the wheel well. So you have a completely flat underfloor, except for when you're going, your suspension has to travel a bit. But you can go to extremes with this technology and really reduce the drag. And design is not a constraint. It's more a matter of serviceability. If you take your car to the garage,
this is an example on how EV can enable something for the aerodynamic of a car. Very typical example.
Exactly. Yeah, indeed.
So we talk about a little bit some case study you have made, because at AirShaper you are doing all the time some tests, and you publish on your website. I have to mention you have also your YouTube channel where you describe a lot of these tests. So we have selected together 3 cases you can talk a little bit about. So we continue with the Volkswagen ID3. So on this example, I have chosen just one picture of everything you have made, but you made a lot of work.
Yeah.
If you can talk a little bit of what you have done.
So there's 2 different things when it comes to aerodynamic simulations. One is an analysis to just understand what the airflow is like. You take a car, you analyze the airflow, and you start to interpret the results yourself. Another thing you can do. The slides are there. The slides. Another thing you can do is to actually have the software optimize a certain shape, and that's what we did in this case study. And that means that on our AirShaper platform, the only thing we need to do is to provide a box, a 3D design space around the car, and then tell the software within this box, you can play around with the shape as you like, and we only ask you to achieve or improve a certain goal. In this case, the goal was to reduce the aerodynamic drag on the vehicle. And then after, I think this was 10 iterations, the software started to morph the rear of the car, that's the design space we defined, to have the air exit at a lower angle and play with the pressure recovery that you have at the rear of the car. And this is very interesting because it comes up with shapes that are better in terms of aerodynamics, but it doesn't look at design constraints. So after this, a designer would actually use the results and say, yeah, this doesn't look too good, but maybe I can actually use part of this or be inspired by this to actually make something that fits in between the normal shape and the optimized shape. And very often you get very unexpected suggestions from the software, which help designers to actually go into a different direction and come up with new shapes. And I think in this case, we had around or over 6% drag reduction by
6%,
applying,
okay.
which is really a lot on a car. Of
Yeah,
course,
that's a
this
lot.
has compromised visibility, this compromised packaging, this compromised the space in the boot of the car. Still, it's very interesting to show what is possible, because as long as
Yeah.
you don't state what the benefit is of a certain change, design change, designers don't want to implement it. If you just say, I think it will be better, that's not enough. So quantifying it is important.
So another example you made was on more pickup truck, something
Yes.
very different and not obviously optimized for aerodynamic, I'm going to say.
Yeah.
So this is on the Ford 150. I don't know if it was a Lightning, but anyway, it doesn't change the discussion here about the aerodynamics. So I know you made a lot of tests again here.
Yes. So what we did here was to take one of the icons of the United States in terms of the most popular pickup truck that they have, which is the Ford F-150. This was indeed the combustion engine version, but the latest one. And we tried all kinds of things, typical tricks that are being applied to reduce drag. The most effective one was to apply a rear cover, because on these pickup trucks, as soon as the airflow has passed the cabin, it's out in the open and there's no surface to follow, and the air becomes turbulent, it dives down and hits the tailgate of the truck and so on. So that's really bad. So adding a rear cover reduced drag by almost 15%, which is massive. And it's not a surprise that the base shape of a Tesla Cybertruck is exactly that. It's a slope at the front and it's a slope at the rear. So that's with a very good reason that they have this shape, and very likely this was inspired
But
by
this is the first time I
aerodynamics.
can hear an explanation for this strange shape
Yeah.
of.
Yeah.
Okay.
Yeah, this is called pressure recovery. It's like when you're holding soap and you squeeze, it jumps out. It's the same with the car. As soon as the air has passed the midpoint and needs to contract again, if you do it properly, it kind of helps to squeeze the end of the car and push it forward to recover some of the drag you created at the front. Of course, you can never have net positive effect, but it does help to recover, and this is called pressure recovery. Then the flat underfloor, we discussed it before,
Yeah.
just making it smooth, reduced drag by over 3%, which is in line with what Volkswagen stated, the 0.01 to 0.025. So all kinds of optimizations. And the one you're showing here is the Aptera.
Yeah, it's more extreme design, I would say, because this
Yes.
look like more futuristic,
Yes.
car. And it's from real people designing this, called Aptera, right?
Yeah, indeed. So what Aptera did was to say, forget everything. We're going to start from scratch and design a car for ultimate efficiency, because the more efficient the car is, the further you get on the same amount of energy. So they started with a drop shape, which is clearly what you see for the main cabin, and then put the wheels next to it. That's the basic concept. And they achieved a drag coefficient of 0.13. So if you look at the Mercedes EQXX, which is 0.17, then this is still far beyond that figure. And they have a range with the full battery option of 1,000 miles, which is what they're claiming. So that's a huge figure.
So let's talk a little bit about some of the trends we observe in aero and EV technology. So there are several. The first one we can really discuss from this slide is we discussed together that there are two different ways to see the aerodynamics. Some few things based on what I'm going to say normal car, traditional way to design and maybe improve, and some of this very futuristic stuff. Do you believe they can develop in the future? I wonder also because homologation, and it's not the way we see car for the moment, but I don't know, maybe in 10 years we will see car like that, maybe.
Yeah, so indeed, there's seem to be at least two different groups. One group is trying to make existing cars still look normal, but as aerodynamic as possible. And I think the Lucid Air, the Tesla Model S Plaid, and so on, they fit into that category. Look as normal as possible, but still behind the scenes with all kinds of small tweaks like air curtains and so on, be as aerodynamic as possible. And they're around 0.2 in terms of drag coefficient right now. And then there's the other group, which says, no, we're going to go for the maximum efficiency for the type of vehicle we have in mind. And then you have a Terra with 0.13 for this car. I see the EQXX and the Lightyear also in that second category, because the design is really a compromise. It's a very long tail going down. It doesn't look like a normal car. You can argue that it's still pretty, but it's different. Sorry?
The IQXX is still going to be a true car, I mean. So
yeah. So it's a true car with true functionality, seating for people. So it's a proper car. But design-wise, they said, let's go to the extreme and let's compromise and move away from the default design language of a car. So both exist. And in terms of homologation and so on, the Aptera, like you said before, it's not going to be easy. You have the suspension sticking out, you have wheel covers. So in terms of pedestrian safety, this is a challenge. They will face quite a lot of challenges.
So talking about the IQXX, because you talk about this car, do you believe that the aerodynamic are going to help some of strategy for battery? Because the IQXX, they get the particularity to get air-cooled battery, which is not something common for now. Yeah. And it's also related to the fact that you can design the things that can enter the car and make the cooling different. So do you believe that this aerodynamic can also help some of the design, such as thermal management, such as air cooling, to get trendy again? Because again, I just want to mention that air cooling save you a lot of consumption, because you do not have the same fluid to move for the liquid cooled and so on. So you get a lot of benefit to get air cooled, but obviously it's slightly different technology. And here maybe the aerodynamic can help to get more flow, really best use for air cooled battery, for example.
Yeah. Maybe there's also a contrast between the first electric cars to break the market open. That was Tesla that mainly did it, and they went top down. They started with a super sports car, then the Tesla Model S with high performance. They needed the numbers to convince people this is really cool. Apart from the environment, this is really, really cool. So you needed a lot of cooling. But if you take a different approach and you say, no, this is going to be an eco car, we are not going to provide 700 horsepower. We're not going to provide super fast discharge rates to accelerate like crazy. Then you can take a very different approach, just like Lightyear. If you limit your power rating, you can limit the total amount of cooling that you need, because very often it's just 0.something% of the time that you need the top cooling performance of a car. All the rest of the time you're just cruising. It's only when you're accelerating to 60 that you need it. So if from the start you say we don't need that much cooling, you have a lower cooling need in general, and then indeed you can start to work with natural airflow patterns instead of forcing the air through big coolers. You can use more natural airflow patterns, like use the high pressure at the front and some low pressure area somewhere else on the car to evacuate that airflow, and it opens up a lot of possibilities. And if you can combine this with the natural airflow around the car, on the EQXX you have these ventilation holes and so on. If you can channel the air in the right openings to fill a wake somewhere, or to help reduce or increase the pressure in critical areas, then yes, you can make the system very efficient.
The last trend I wanted to talk about is the fact that for now, most of the electric vehicles we have are a lot of SUV. Yes. And we see now a lot of US people making like the GMC Hummer and other big truck. They're obviously very big car, and I'm going to say maybe not the most elaborated in terms of other technology, especially the aerodynamic. Do you believe that we can keep this trend and see a lot of SUV and big cars, but if we work on the aerodynamic, gain something maybe?
Well, I mean, it's the general illusion of climate change, right? Can we maintain our life standard and just do some small tweaks, install some solar panels, and just continue our lives as we're used to? Or are we going to start over and do things differently? I think it needs to be the second one. But if you talk about SUVs, whichever way you look at it, it uses a huge amount of energy to move forward. Whether it's electric or combustion engine, it's a big, heavy vehicle. Heavy means you have a lot of rolling resistance on the car.
Mhm.
If it's 2, 3, or even more tons of weight, there's a massive amount of energy involved in overcoming the friction. And it's still a big car as well. SUVs are simply big and they're high above the ground. They have big wheels, and this is very, very bad for aerodynamics. So, if you claim to build an aerodynamic or eco-friendly SUV, I don't think that's possible. If you really care for the environment, a smaller car, whether it's electric or combustion engine, is the first step. And if you can then make it electric, use solar energy and so on, then that's yet another benefit. But an SUV is per definition not an eco car, not an eco-friendly car.
So we are going to move on to, I hope, some question from Tom, and get back later. So Tom, do you have any question from the audience?
Hello. Unfortunately, we've been hit by LinkedIn technical issues again, but we do have a number of questions that were submitted beforehand, plus a couple of my own. I guess extending the point that we were just discussing with regards to pickup trucks, do you think that the increasing volume of EVs and interest in range will drive a resurgence of the saloon sedan body style?
Well, let's hope so. I think they look pretty good. I like those saloon body styles. It could be. And we had an interview with Hendrik Fisker of Fisker, designing the Ocean and other cars. And what we didn't include in the interview was a bit where he said, well, we asked him, how efficient is it? Did you focus on aerodynamics because you claim to have built the most sustainable electric vehicle on the planet? But it's an SUV, so per definition, I think that's the wrong statement. But then we asked, how much did you focus on aerodynamics? And he said, well, the whole range thing, the range anxiety thing, battery technology, I think this is a short-term problem. We're now struggling to get enough range, and people are scared of it. They have to get used to it. But in the future, we'll be able to fast charge, so the problem will go away. We'll have better technology. So he said, I don't want to compromise my design too much to actually get to higher range figures, which I found a bit disappointing coming from someone claiming to build the most sustainable EV. On the other hand, I think in a way he's right. We're probably going to overcome the main hurdles that we have in terms of range. And in the short term, probably we're going to see more cars like the Lucid Air, which are super streamlined, the EQXX, which takes it to extremes. And probably after that, someone else is going to say, well, we've covered the technology to extend the range again. Now let's do something crazy again with the design because we have the freedom again. So in the short term, yes, I think it will influence design a lot. In the longer term, it might be that we move away again.
Yes, it'll be. I think it'll be interesting to see what happens, won't it? I guess you can engineer the most perfect aerodynamic vehicle in the world, but if it doesn't look good, no one will buy it. So
exactly. Yeah.
It makes zero difference at the end.
Still very true.
Yeah. Right. The other question we had was about CD focus. So, are there any issues from an aerodynamic perspective in focusing entirely on CD? So, with regards to trade-off against coefficient of lift and maybe sort of side wind behaviors as well. And is there anything that can be done to mitigate it?
Yeah. Well, just as an example, very ironically, if you make a car bigger, you can actually make the CD go down in some cases, because if it's bigger, you can increase the good areas, the smooth areas, and they proportionally gain in terms of size versus the fixed size bad areas like the wheels and so on. So ironically, increasing the size can reduce CD in some cases. And that's something you have to watch out for, that you don't focus too much on CD, but always look at CDA. And indeed, if you have a car and you want to lower the drag, what you typically want, especially the sedans that you mentioned, Tom, is that you want a very long, gentle slope at the rear of the car, which is good to contract the air and close the wake behind the car. But what also happens is that you create a low pressure suction area at the rear of the car and a very large surface, which generates a lot of lift at the rear of the car. So this can actually generate lift at the rear. And if you have lift at the rear at high speeds, this can become very wobbly. You can get into oversteer in some situations. So yes, if you focus too much only on drag, you can compromise actually performance and stability and safety of a car.
It's all a trade, isn't it?
Yes.
I guess that links nicely into another question actually around brakes. So given that we've talked about those being quite dirty areas around the wheels in terms of airflow, are there any additional opportunities with EVs, given that the conventional friction brakes are used to a lesser extent?
Yeah, that's true. So if you don't use the normal brakes as much, the normal brakes, they dissipate energy locally. Within the wheel rims, the brake pads are heating up and you need to dissipate this energy, which means you need enough opening on the wheel rims to evacuate this heat. If you do regenerative braking, the energy losses, if any at all, they're small. They happen inside the battery, inside the motors, the inverters, and so on, which are actually usually away from the wheels. Which means you can have more closure of the wheel covers. So if you have more area of the wheel covered, there's less turbulence generation when the wheels rotate. And this can clearly provide a huge benefit, like we saw on the covers for the Tesla Model 3 and other models. 3-4% improvement in drag is huge. So yes, there's lots of benefits. Still, you need some opening. If you're gonna brake at some point, you still need some escape route for the heat to get away.
So yeah, so less chopping up the air on the way through. One specific question around the Kia e-Niro. So recently, there's been a facelift to the Kia e-Niro where it appears that the powertrain package has remained the same. So same battery, same amount of usable energy, but the range has gone up. And it looks like that was an efficiency focus. And if you look at the CD pillar area on that vehicle, they've moved to a vented CD pillar. So I wonder if you could describe how that might work and how that might benefit the coefficient of drag.
Yeah,
the range.
If you can pop up an image, that would also be nice. But in general, what you can do, like with air curtains, for example, at the front bumper of a car, you accept air which is coming in at the front of the vehicle, and normally this hits the vehicle and this creates a pressure buildup. But if you can use some of that air and channel it and accelerate it through a small channel and then exit it at a strategic location, like just in front of the tires, the front wheels, and make that jet go around the front wheels, then this shields the wheels and reduces the churning losses that you have caused by the wheels. So this is called the ventilation drag on the wheels. So if you can reduce that by shielding the wheels, then this is quite useful. And you can apply these tricks in various locations on a car to just accept air and then channel it and make it exit at a crucial location. Even the Ford GT, if you remember the latest model, behind the cockpit, it had like these two narrow channels where the air would fit in between the cockpit and the wheel wells, which is really nice because you reduce the cross-sectional area of the car there and allow the air to already contract just behind the cockpit before you reach the end of the car. So there's a fresh jet of air hitting or entering the wake behind the car, reducing the drag that you have. So yes, proper.
Something like the form of a Formula One car under the skin, isn't it, in that area?
Yeah, exactly. Yeah, even Lotus applies it these days, even on their SUV.
Yes, the Avaya.
But they call it a porous design strategy.
Yeah. Great. I think that brings us to the end of the questions. So I guess the first thing to do is to say thanks very much, Wouter, for joining us today.
Yeah, thanks, Wouter, for coming
through that.
Very interesting topics. I hope I have really enjoyed, because I learned quite a lot of things. So thank you very much.
You're very welcome.
And you mentioned that Wouter get also a nice blog and a nice YouTube channel where I explain a lot of things on aerodynamic, how to use AirShaper, publish tons of information. So I highly recommend to have a look to the AirShaper YouTube channel.
Thank you very much, Cecile, and thanks for organizing this, Cecile and Tom. It's been a pleasure to be featured on your channel.
Great, and thanks, Cecile. And as Cecile mentioned, we're also on YouTube, so don't forget to check out other videos, and also send us your requests for what you'd like to see covered in future episodes. Hopefully, we won't have so many technical issues going forward. I'm fixing those.
Okay.
Thank you very much.
Thanks,
Bye,
everyone.
Bye-bye.
Bye-bye.
Bye.